So hello friends, uh, this in this tutorial we are learning about the boundary conditions. Okay, so I have started about the geometric field, and I am giving some introduction about the geometric field, and parallelly I am thinking that we should start also working with the development of the new boundary conditions. Okay, so in this way this lecture series will not be boring. So parallelly, I'm also explaining the basic concept of the geometric field classes, and then how this geometric field is related with the boundary field. This everything I will discuss in upcoming tutorials, and parallelly we should also start working with the creating a new boundary conditions. Okay, so here I am going to develop some new boundary conditions, and before start beginning that class, we should know that there is another utility you can say, like the swap for home and the code stream. So using these two utilities you can also develop new boundary condition whatever you want to work for you. And maybe in this tutorials series I will also explain about the swap perform and the code stream. So generally if you developing a new boundary condition in OpenFOAM. So generally boundary condition present in zero folder in the form of the dictionary that you already know. Okay. So the for that purpose this dictionary is to be read, and then the information of the dictionary is to be passed to the boundary condition constructor. Okay. So that is why I have already explained about the dictionary tutorial in the last tutorials. So generally there are four functions that is important for development of the boundary condition. So that functions are the update coefficient and value internal coefficient, value boundary coefficients, gradient internal coefficient, and gradient boundary coefficient. So these are the five important functions that are needed to understand. However, the other four are just to complement the update coefficient functions. Okay, so main function is the update coefficient, and these are just to help to update the coefficient of the given patches. So, okay, so here I am going to just discuss about the first function, that is the update coefficient, and other functions we will also discuss parallelly when we have more idea about the geometric field and the fvPatchField in more details. Okay, so here I am going to just give an idea about the update coefficient. Okay, so here whatever the boundary condition I am going to apply, this function is important for you. Okay, so this boundary condition we are going to update, that is the u equal to u max 1 minus y minus c to the power 2 and upon the r square. Okay, so this is the, suppose this is the patch is given here. Okay, so y is the face center of the every faces. So you can see that this is the patch and there are number of faces you can see. Okay, this is the 2D face. So this is the boundary condition that we are going to apply. Okay, so let's go to the terminal and let's start and see how you can develop your own boundary condition. So here you can see that I am in the folder of the understanding boundary condition, and I have created a folder for developing new boundary condition. Okay, so I will open this folder in a terminal, and I'm going to type OF6 environment. So OF6 environment has been created. Now if you type form new BC, okay, so this is going to give me how this command can be useful for you. Okay, so like we used to type form new app to create a new solver, a new application. Similarly, you can type form new BC to create new boundary conditions. Okay, now if you type the so let me just clear the screen. Now if you type form new help, okay, so you can see that it is giving me some of the options here. Okay, so first it is saying that it will create a directory of the source and compilation files where this .c and .h folder is going to present. Okay, and there you will also find a make folder. Okay, so this is going to create a this kind of folder structure. Okay, and the compilation of a library will happen in this form user limpid. Okay, so this is complete about the this command that is seen in the screen. Okay, now if you want to what kind of boundary condition you want to create. Either you want to create a fixed value type of boundary condition or a mixed value type of boundary condition. And then here is given that what kind of boundary condition you want to use, like if you want to use for a scalar or vector or tensor. So we are applying a parabolic condition for a vector quantity. So for velocity it will be vector. So here we are sure that we want to develop a boundary condition for the vector. So remember that I have told you that whenever we are applying some fixed value to a given boundary condition, then it is a Dirichlet type of boundary condition. So therefore, it will be a fixed value type of boundary condition. Okay. So now I am going to use this command foam UTC. Okay. Then I am going to use the fixed value because I am going to apply the Dirichlet kind of boundary condition. We are specifying as some value to a given patch. Okay. Remember that the zero gradient type of boundary condition is generally the Newman type of boundary condition that we are not going to use. We are specifying some value to given a patch. That is why it will be a fixed type of boundary condition. And since we are going to use for a vector, so that is why we are going to use the -v command. Okay. Remember here that is the form UBC. F is for the fixed value and V is for the vector, since we are creating the boundary condition for the velocity too. So this will be vector here. Now I am going to give the name of the boundary condition. So I am going to create a boundary condition with the name of the my velocity. Okay. If I press enter, you can see that it has been created a directory with the name of the my velocity, and it has been added to file that is the .c and .s folder. Okay. So if I open ls command, and it can show you in the folder also, so you can see that this folder has been created where .c and .s folder has been created, and there is a make folder. And if you open the this file folder, okay, so you can see that the .c folder is one.c, and this will compile to the home user libbin, and here it is going to create a library that is the lib my velocity. Okay, so let me open this .s folder in a terminal. Okay, let me open it in the GD editor. So if I open here, you can see that it has been derived from the fixed value fvPatch vector field. Okay, so remember that I have told you that whatever boundary condition we are going to develop, that is generally derived from the basic folder of the finite volume field folders. Okay, so if I show you on a terminal again, let me go to the this home folder. So if I go to this 6 folder, and if I show you in src folder, and there is one finite volume folder will be present, and here in fields and then fvPatch fields. So generally whatever boundary you create, that is going to derive from the this given folder. Okay, so here you can see that fixed value fvPatch field is present. So generally whatever the boundary condition you create, that is going to derive from this basics folder present in this folder. Okay, and now if you see that there are different data is present. Okay, so this is the private data. Okay, that you can access to use in your boundary condition definition. Okay, these are the type name that you are going to specify if you want to apply this boundary condition, and these are the different constructor is given here. Okay, and this is the sum fact functions for the mapping purpose. Okay, and this is the function that we are going to update for our boundary condition, that is update coefficient. Okay, so this is the function that we are going to update according to our given formula. Okay, now first let me just modify the private datas and the .c folder. Now before going to the development part, let's understand first how this boundary is going to work. So this is the boundary that we are going to apply. Okay, so this u max is just some scalar quantity that we are going to ask from the user, and now this y minus c is a, that is the y is related to the face center of the faces. So these are the different faces you can see on the screen. Now this face centers will be vector field. Okay, so this will be a vector field of the centers of the given different faces or patches on the given screen. Okay, so this will be a vector field, and this C, that is the center of the bounding box, that will be the maximum box minus the minimum box. That is also will be a vector field. Okay, so before doing the squaring of this quantity, we need to take a dot product with the some vector quantity, take a whose magnitude will be unit. So here that r square, that is the radius of bounding box, that is also the maximum minus minimum of the vertices. So here also before squaring this quantity, that is the r square, we are going to take a dot product. So here what I mean, that if you want to apply this formula for the given phase, so this is the what we want to implement. Okay, so this is the plane. You can see that I am working in a xz plane. So if I want to specify some boundary condition, that will be in the y direction. So the component of the velocity should be in the y direction. So for that purpose, we need three quantity. Okay, these three things should be user defined. Okay, so that is the first one is the magnitude of the u max, that is going to some scalar quantity. And for example, I am here giving one scalar quantity, and it is equivalent to 2. And this 2 quantity, that is going to be the unit normal vector. Okay, so what is this 2 quantity? So first, a vector quantity is needed, that is going to multiply this y minus c or to the value of the r before doing the squaring of this quantity. So after multiplying this quantity to this y minus c or r, that is going to give me a n scalar quantity here. Now you can subtract that scalar quantity from 1. Okay, and after that you are going to apply with the multiply it with the u max. Okay, and once you multiply with u max, okay, then this automatically this complete quantity will become a scalar quantity. Now the problem is that it is the scalar quantity, but velocity field is a vector itself. Okay, so after that, this whatever the scalar quantity you are going to get here, that you are going to apply with the this quantity. Okay, so you can see that this vector is the 0 1 0. So automatically whatever the scalar quantity will multiply, this will become that 0 into the that scalar quantity. Suppose you are finding that some value v, so this will be 0 v 0. We are going to take three values, that is the u max, y normal, and that is a normal vector. Okay, so this three quantity that we are going to ask from the users. Okay, so here out of these three, we have two vector and one is the scalar. Okay, so let's go to the terminal again. So first we are going to do modification in the .h header folder. Okay, so here we are going to take two vector field. So that is why we are going to erase everything. We don't need a time also. So we are also going to erase this. We are just going to need a scalar field, that is the u max. So here I am going to write it as a u max. We are going to ask from the user, that is the u max. And second, we are going to ask from the, that is the y vector. And third one that we are going to ask is the normal vector. So this two quantity, that is we are going to ask from the user. Everything other things are the constructor that we are not going to change, and this is the function that we are going to modify based on our condition. Now here if you go to the solver, so since we have removed this function, we have to erase it from here also, because we are not going to need the time value. But sometimes it happens that based on the given time you are going to apply the boundary condition. In such situation you are going to need these things. Okay, so remember that in the object registry class I have told you about the database. Okay, so from here you can see that you are accessing the time value of the from the given database. Okay, that is the concept of the object registry. You can watch my video. Now let's do the modification in the constructor. So here we are going to need a scalar field, and other we are going to need a two vector field. Okay, so here you can see that these are the different quantity that we are going to need, that is the UMass, that is a scalar quantity. So here I can put the UMax. So that is the constructor based on the default value. Sometimes your user don't provide the value for a given the variables in the private private data. So in such cases situations, these are the default constructor that is going to work here. Okay. So here y dash that we are going to specify. And remember that this y dash should not be a zero magnitude. Okay, so it should be 100 or 011 or 001 or 010. So some magnitudes, one magnitude should be there. Okay, so for example, if we are going to specify 100, and similarly, we are going to specify for the normal vector, and suppose here I am going to give 010, and don't forget to remove this comma from here. Okay. Similarly, here I am going to do modification. So here also I am going to need one vector quantity. So here this will be Umax, and I'm going to ask from the, that is the constructor based on the dictionary. So you are providing some dictionary here, and based on the dictionary, you are providing some dictionary here, and based on the dictionary, this constructor is going to ask for the value. Okay. So for example, when in the dictionary, if you specify Umax value, that value is going to be stored as the Umax in the this constructor. Similarly, whatever value will specify for the y, that is going to store in this y dash variable. Similarly, I am going to ask for the normal vector. Okay, so I can give it as a normal vector, and that is going to store in the n dash. And here again, don't forget to remove the comma. Okay. Now here also again we are not going to remove everything, and we are going to again add the Umax. Okay. You are also again going to add the Umax. So these are the different constructor that you have to modify before going to the update coefficient function. Okay. Again here I am going to need y dash. Again I'm going to need that f n dash. Okay. Here I can do the comma. So this is also based on the PTF. So I'm just copy this, and here I'm going to just print everything. Okay. Here this is also based on the PTF, you can see. So again I'm going to just copy paste here. Okay, so these are the different constructor you can see, and rest thing is automap. You are not going to do anything, but this variable, that is the field data that you have to map, that you should remove from here. Field data that you are not using anymore now, so that is why I am removing from here. Now this is the functions that you are going to do modification. Okay. Also, if you want to do write entry, that you can do here. Okay. So for example, I am also specifying the UX. So here I am going to ask for the Umax to print on the screen. Okay. And here I can just write the UY. Okay. Similarly, I can ask for the normal vector. Okay. So that is all about the constructor. Okay. So before going further, let me just comment it out and let me compile and see that is it showing any error. then after that we can do the modification to the main function of the. Okay, so if I go to the my velocity and I can clean and I can do the double make. So hopefully should not show error, but here I'm getting some error because it is showing that it is not declared due to the some syntax error. Okay, so here I am typing two times the or the dash keyword. That is why it is showing the error. Now if I again do the clean, I can double make. So you can say that everything is working well. Now we can do the modification for our coefficient part. So friends, this is the boundary condition that we are going to implement. Okay. Now we will know that this umax that we are going to ask from the user. Okay. Now the this two quantity that we have already asked from the user also, that is the y and the normal vector that we are going to use, but before that we need to know that what is the range of the bounding box. Okay, so we need to know that the bounding box range, I mean to say that. So first we will have a patch, so we will get to know the information of a given patch. Okay, then from the information of the given patch we are going to ask for the what are the faces this patch is have. So this patch has what are the faces it is referring to, that we are going to ask again. Then after that we are going to ask for the points related to this patch, that is known as the local points in OpenFOAM. Okay. Now from these local points we are going to ask for the minimum and the maximum value. So how we are going to achieve this? For this purpose, let me show you the source code of the OpenFOAM. Okay, if you go to the OpenFOAM 6 version and if you type the bound box, okay, so here you can see that this is the header file related to bounding box. Now if I open here, now here see that this is the something that is related to the bounding box. Okay, so to construct the element of the bounding box we are going to need the point field. Okay, so this is we are going to need, that is the point field, but we have the information of the patch, we have not access to the point field. Now from the patch field we are going to generate the faces, and then from faces we are going to look for the points, then from the points we are going to look for the this bounding box constructor, and then from that constructor we can ask for the these two function, that is the minimum and max function. So if I here type fbs patch field h, okay, so if I open here this fbs patch dot field dot h, now here you can find a function. So you can find this function that is going to return me a patch. Okay, so this is going to return me the patch of the given fbs patch field. Okay, now here you can see that this is returning a patch. So here you can see that the return type is the fp patch. Okay, it is not giving me the information of the faces, it is giving the information of the complete patch. Okay, so that is why this type is the fb patch. Now here you can see that there is another header file that is already used, that is the fbpatch.h. So if I go to the fbpatch.h, so this is the header file for the fbpatch. So if I type here patch here, now here you can see that this is giving me the access to the faces. Okay, because it is returning the poly patches. Okay, so here we are just getting the access about the patches, and here we are accessing to the different faces of a given patch. Means we are going to call for the patch. Okay, so that it will give me a access to the given patch, and again if I call the same function, then it is going to give me the faces of a given patch. Now there is a function name as the local points. that is going to give me a complete access to the vertices of a given faces. Okay, to give construct a constructor that is the bounding box with this information and the information that is given on a oxygen. See here that this is the bounding box source code, and here you can find that this is the constructor we can use here. Okay, so we are providing a point field, okay, and we are providing a whether you want to reduce or not, that is something bool information that we have to provide. Here I can write bound box, and maybe we can put some name bb, okay, and here this local points that we have provided, and now we can type that is the true. Okay, so this constructor we can provided here. So friends, we have found out the bounding box. Okay, now using this bounding box, we can calculate the coordinates of a given this patch. Okay, so we are going to calculate the midpoint of a given coordinates. Okay, so for that purpose, we have to calculate the vector. So this coordinates should be a vector quantity. Okay, now let me just put as a mid coordinate. Okay, so this we are calculating the mid coordinates of a given. So what I mean to say that this is the max coordinates and this is the min coordinates. So when we take the sum of these two coordinates and when we take the half of these two sum up, then it is going to give me the coordinates of the center. Okay, center of this given complete patch. Similarly, if we take the subtract this two quantity and then we half that quantity, then it is going to give me the length of the radius. Okay, that is what I mean to say that mid coordinate will be sum of these two max and min, then taking the half, so we can do this 0.5 multiply this should be bb dot max plus bb dot min. So we are calling these two functions, that is the max and min, and using these two functions we are going to calculate the mid coordinates of a given functions. Okay, so if you go to the this source code of the bounding box, and then you can find this mix and man function, mix and max and min function. Okay, so this part we have done, we have calculated this c. Okay, now using this c we can calculate one vector field. Okay, so we can calculate this y minus c. So let me put that yc equal to, and I can calculate y minus this mid chord. Okay, so it is going to give me a vector field of the subtraction of this y minus mid chord, but y is the face center of the every given face. Okay, so here y means that face center of the every faces of the given page. So if you remember my tutorial from the class of the understanding the mesh, then I have told you that if you want to read the face center of a given page, then this quantity is going to helpful for you. Okay, so this quantity you can call the every face center of a given page. Okay, then we can subtract it, and then we are going to get this yc. Okay, now we have calculated the yc, and we have to calculate this two quantity as a scalar field, because we cannot do the square of a given vector field. So for that purpose, remember that we have taken one vector from the user side. So y dash will going to convert this vector field into the scalar field. So I can write the scalar field. Now I can maybe put this as a temp one, and then we are going to do this yc. Okay, and then we are going to take a dot product. Okay, so this we are taking dot product using this yc into the y dash. So this first term, the above term, we have calculated like that. Now in at the denominator we have the radius. Okay, so radius we can just subtract the max and mean, max minus mean. Okay. And then if we can divide here, so if you divide this quantity by 2, then we are going to apply here that 2. Okay. So this multiplication should be here. Okay. So this is going to multiply in the denominator, numerator, because we are dividing the this amount by 2. Okay. But one thing you should remember that this is also going to give me a vector. Okay. So therefore, for that purpose, we have to take a dot product with the same quantity that we have multiplied here. Okay. So for that purpose, we are going to multiply this same term in this quantity to get a scalar field. Okay. Now this complete y minus c upon r we have already gotten. Now we have to take the square, and after taking the square we are going to multiply by umax. Okay. Now if you want to update something for a given patch, this update coefficient will only work if you use the operator up equal to. Okay. So if you see this code here, okay, that I have opened from this derived folder, that is the fixed mean kind of boundary condition. So if you see here, there is a operator that is the equal to operator. So this is a very important operator. Unless and until you are not going to specify some values here, it is not going to update the value of a given patch. Okay, so therefore we need to specify whatever the values you want to give for a given operator. Okay, so these things I can write here. So remember that I am copying this operator from the fixed value fvPatch vector field, because we have already derived this in the given this my velocity fvPatch vector field. Okay, so that is why we can use this operator in our library. Okay, now this operator we are going to specify here. So first we need to call this umax. That is what we are asking from the user side. Okay, so this umax will be written here. So umax. Okay. Now remember that this whatever the multiplication we are going to do, this quantity will be just a scalar quantity. Okay. Now this we are providing this boundary condition for a velocity. So velocity is a vector quantity. So based on that purpose, we are asking from a user that is the normal vector, normal unit vector. So when we multiply this normal unit vector with a scalar quantity that we are getting, then it is going to convert into the vector form. Okay, so this things we are also asking from the user. So now this part is done, this umax part is done, and now we have to finish this part. Okay, so for that purpose I can write 1 minus. Okay, and this temp1, so temp1 is the completely 1 y minus c upon r. So we can do the square of this quantity. Okay, now think. Now this is the complete boundary condition that we have derived here. Okay, so this equal to operator is going to update the whatever the values we are getting here. That is going to update it to the every faces of a patch. Okay, now let me compile here. Some error I am getting. Okay, so this should be patch. I am typing misspelling something. So this is PATCH. So here there should be one semicolon. Now I can do the wclean.all wmake. So there is some error I'm getting. Okay, so these things we cannot put as a reference. We cannot put a reference, but now I think it should work. Okay, so everything we have done here. we have developed our boundary condition. Now we can just develop a test case. So we can copy when any test case from here. So maybe let me, I can copy this picture daily test case. Okay. So I can put here. Okay. Now let me first show you the meshing of this test case. First we have to run the meshing command, that is the block mesh, and then I can just type the paraFOAM. So you can see that this is the meshing command. This is the inlet. Maybe you can provide inlet velocity here as a parabolic. Okay, so here you can remember that the x component should be present here, and in y z direction we can use for the scalaring purpose. So see that here we need to specify two vector. One vector should be in the direction of x and another vector should be either in the direction of y and either it should be in the direction of z. Okay, I can go to the U folder and here I can put what is the type of the field that you can know from the S folder. So here you can show that this is the type name that we are going to use. So it is the type name, that is the my value, and here we are going to provide some values. Okay, so for example, what are the values you want to provide, you need to provide that. You can go to the C folder and remember that we are using the constructor that is reading the value from the dictionary. Okay, so here you can say that this different three values we are going to specify, that is the umax. Okay, so we are going to give the umax. Okay, now next one there should be y, and third one you can specify the normal. Okay, so this is the normal that we are going to specify here. Okay, now umax we can give 1 meter per second. Okay, this y max you can put normal vector that is either in the y direction. Okay, and this normal vector it should be in the x direction. Okay, this is the whole idea about. But when we are going to run this test case, this solver, that is the simple form, it is going to show me an error. Okay, because we have not linked the library, that is why it is going to show me error. Okay, so you can see that it's saying that I don't know what is the my velocity, this type name I don't know. So for that purpose you have to go to the system folder and then to control dict, and here you can attach your library, that is the libs, and the name of the library should be what you have compiled on the screen. So this is the name of the library that you have compiled. Now you can source it in control dict. Okay, so this has been sourced. Now you can run your solver. So it has been converged out. Now we can see the result in the paraFOAM. Here is the geometry and here it is the velocity solution. Okay, so you can see that this is the parabolic type of boundary condition you can observe. Okay, so let me go to the starting. So here you can see that this is the parabolic type of boundary condition you are getting. So this is you are getting the parabolic type of boundary condition at the inlet, and that is why you are getting this kind of a final converged solution. Okay, so I think this video is helpful for you. Okay, so this is the whole idea about how to develop a boundary condition in OpenFOAM. So here I have just given one example of the parabolic velocity field. Okay, we are going to develop some more advanced boundary condition, and parallelly we are going to also discuss about the geometric field. Okay, so watch this complete series on the boundary condition, and I am sure that whatever the confusion you have about the programming aspects of the OpenFOAM, those aspects will be clear by watching this complete series of the boundary condition. So thank you all for watching this video, and please subscribe my YouTube channel and also share this YouTube channel to your friends. Thanks to all of you.